All right, welcome back to the coding of the proof of concept application for per pixel collision detection. I'm sure you guys remember this whiteboard screen from just a few videos back where we were talking about the overview of the entire process. Now in this video, which is going to be a short video, what Logan is going to do is demonstrate how we can now normalize this rectangle that he managed to get in the last video. We want to be able to normalize it against each of its respective sprites, so that we can use that information to sample out the correct pixels in each of our textures. And then we're going to wrap this video up with drawing those two textures, those two sets of pixel data on top of one another in the upper left-hand corner.
Just to verify that we are indeed looking at the proper portion of each texture.
Exactly. So we'll grab those little parts of the textures and draw them. So that's pretty much what we're going to be doing. Logan, I'll go ahead and hand it on over to you.
All right, let's go back over to Visual Studio and let's get started. The first thing, of course, that we'll need before any of this can work is the normalize method. So here we are in the actor class. I'm going to jump in right below the intersect method. And I'm going to put in another method called normalize bounds. And I'm actually going to change my mind here. I'm going to drop it in above the intersect method, just kind of following these in the way I want to see them in the final version. All right, but this method is going to take in a rectangle, any arbitrary rectangle, and it is going to normalize that rectangle against this current actor's position. That means that this method is going to be instance as opposed to the static one that we used for the intersect method.
That's right.
So this is going to be a public method returning a rectangle, which is called normalize. I'm going to call it normalize bounds. It could also be normalize intersection or whatever you would like. But I had named the bounding box bounds from before, so we'll just stick with bounds here. And the rectangle that we want to take in, we'll use a parameter called rect. Now, from that rectangle, we need to make a new rectangle that is normalized for the current actor's position. So we'll begin with a new rectangle, so returning new rectangle, where x and y will take in that current rectangle and subtract this position's x and y. So let's see, we'll look at rect.y, and then we'll subtract this actor's position, but of course position is a float, so we'll need to cast that to integer. Oh, okay, and I'm just jumping way ahead here. Well, a field ahead here. We're actually looking at x first.
Yeah.
So I was about to define what was probably going to be a
very
flipped,
interesting, yeah.
An x and y flipped rectangle. So yeah, we instead want to look at the rectangle's x and subtract the current position's x. Once again, that being a float means we'll need to cast to integer first, and we're looking at this instance of position component x. And each of these lines I'm going to drop down to an additional new line just to give enough room here. And now, at long last, for some reason I really wanted to get to the y component here, but now we are in fact looking at the rectangle's y minus the position's y.
And again, on the whiteboard, this is exactly what we had drawn out in the first video of whiteboarding the overview.
Right, where you had done the two subtractions, where you had 80 minus 50 gave 30, and then 80 minus 80
right,
gave
where
0.
I started to get tripped up because I wanted to take the two different guys and add them together. Yeah, I remember.
But, all right, so that takes care of the complicated stuff, the normalization between position, because width and height remains unchanged.
Exactly. So this was the part on the whiteboard where I was trying to do some more math, but there was no reason.
There was no math left to do.
It's already done.
Because as you can see here, we're simply, you could say, passing through the values for width and height for that rectangle.
Exactly.
So, I mean, that's it for normalized bounds. All very simple, just normalizing that rectangle. But to prove that it's working, let's go back to the game class. Let's go down to debug draw, and let's draw that section, those relevant pixels from each of the textures. So we'll look at sprite batch. We'll tell it to do a new call to draw. Now, the first texture, let's draw from actor 1's texture. And I'm going to position, so we're going to get these two rectangles worth of pixels, but I'm going to draw both of them at the upper left-hand corner of the screen, just as opposed to any other position on the screen. So to do that, I'm going to feed in a value of vector2.0. Now, this is the important part. I'm going to jump down through a few overloads, and we're going to look for overload 3, where we can take in a source rectangle, because now the normalized collision rectangle is going to drive the source rectangle for the call to draw.
That's right.
Sounds complicated, but it's actually easier than that. Here we're looking at actor 1's texture, so we'll normalize to actor 1's normalized bounds for the collision rectangle that we found earlier. And then, of course, we need a color to satisfy the draw call, which will be a color of white. So already I should be able to build and run. Now, granted, this is only going to be one of both of the textures. This is just going to be the ship texture. But as I move the sprite in where would be a collision, we can now see that we're just picking out part of the ship texture. And it should be the part that is relevant to us for collision based on the other sprite.
That's right.
But let's go ahead and normalize the other sprite as well and get its pixels drawing on top. So I'll copy the entire line, simply changing actor 1 to actor 2. So again, same collision rectangle, this time just normalized to the position of the second sprite, or actor 2 in this case. So now, as we move the sprites around, we see we get both textures drawn, but this time we're picking out, extracting just the relevant pixels using a rectangle, but you'll find later that that rectangle is actually very helpful to us when we go to look at those pixels individually.
That's right.
So, I mean, really, that's it for this portion of the video. Again, we just wanted to get the specific rectangle normalized to the texture so that we could get a portion of that texture loaded from a source rectangle.
Okay, and that's going to wrap up this video. In the next video, we're going to, do the final thing, the comparison, pixel to pixel. That wraps it up. Thanks a lot.